Well, I take issue with the title of chapter 2. It's just called probability, but really chapters 3 and 4 have probability in them too. But that's the name of the chapter in the book. So here we go. Some notation and some terms for us. A random experiment, what that means is it's when we carry out the same conditions and we do something under the same conditions, and we're doing it to figure out, what's going to happen, what's our unknown result. And the reason it's called a random experiment is because it will result in, and the word here is different, outcomes, even when we repeat it in the same manner every time. So think about just rolling a die. If you just kind of shake it up in a cup and you do it exactly the same way every time, you're not necessarily going to get the same face value, that turns up when you actually throw that die. We don't do very much with set theory in this course. There's quite a bit more in the chapter 2 than we actually do in this course. So I'm just going to cover what we need. We're going to have two different types of sample spaces. A sample space is the set of all possible outcomes from a random experiment. And there are two types, as I said. We will say that S, that's the letter that we use for the sample space. We're going to say that it is a discrete sample space if it has a finite number of outcomes, like when I throw a die, right? That would be finite. I'm going to have a face value of 1, 2, 3, 4, 5, or 6, or a countably, I should say countably, I have a typo, or countably infinite set of outcomes. Countably infinite would be like integers, all of the integers 0, 1, and then this ... means going on forever. So this would be an example of a countably infinite set. This would be an example, say, for the face value for the throw of a fair die. This would be an example of a finite discrete sample set. S is considered to be what we call a continuous sample space. We're not going to do a lot with continuous, forgot a U, just yet, but it means if we have an interval of real numbers. So if my sample space, probably should have put an S here, S is going to be considered continuous if, for example, I said that S was the set of values between, I don't know, let's say 1.2 and 7. It doesn't really matter, but there's an infinite number of real values in there. So that is a continuous sample space. So here is an example of a discrete sample space that has a finite number of outcomes. So suppose that I'm looking at a message or an email message, for example, and I'm going to call it on time with the letter O, and I'm going to call it late with the letter L. I guess you could think of homework assignments that way too, if you'd like. So what is the sample space S for the next 3 messages or the next 3 homeworks? So we could have all 3 are late. We could have 2 of them be late. So we could have the first late, second late, and the third one on time. Or we could have the first and the third late, second on time. Or we could have the first on time and the second and third late. And same idea here. So here I could have just 1 late, 2 on time, and then we could have all of them on time. So the number of outcomes right here. So if I had to enumerate the number of outcomes, the number of outcomes is equal to 8, 2, 3, 4, 5, 6, 7, 8. And that's a finite number. So there's one example of a sample space. The book talks about doing a tree. You can also demonstrate what the sample space looks like with a tree, but I prefer to use a table notation. I'm pretty sure you've heard these terms before. I'm going to just use the letter E to be the subset of a sample space of some random experiment. And we're going to say that whenever we have 2 events that consist of the union of 2 events, that's going to be the sample space that considers everything in both of them. So they may even have an overlap. But a union is when we're looking for one event or the other. So that is the key word right there, or. We're going to say this is the intersection when we look for just the what the two events have in common. All right, so this will just be what intersects. And then finally, we're going to have something called the complement. And that is anything that is not in E. And usually we represent that with this, I guess this apostrophe, I guess, if you will. Sometimes you see it as E with a capital C up in the top. Right. So let's demonstrate these concepts a little bit. So suppose we've got two parts. Let's say they're identical parts. And they are, we're going to say that like the part passes, yes, if it passes, and N is going to denote that it does not pass. So E1 is going to be when an event will be the event that at least one part passes, and E2 will denote an event that no part passes, and E3 will denote an event that at least one part does not pass. Ooh, well, think about that one for a minute. So the sample space, if I've got two parts, I mean, they're identical. Let's just make them square or rectangular parts here. What would the sample space be? Well, we could have, let me do it this way. We could have both parts that pass. We could have one part, the first part passes, the second doesn't, or the first part doesn't and the second does, or we could have neither of them pass. I thought I'd need more room there. Now, E1 denotes the event that at least one part passes. And so that means here we have two parts that pass, one part, no part. So E1 would be three of these four items right here. We would have two parts that pass because it says at least one, and then one part that passes, YN or NY. So that would be E1. E1 prime is everything that is not E1, right? So everything that is not E1 would just be that both parts don't pass. E2 denotes the event that no part passes. Well, that's the same thing as E1 prime, right? So E2 and E1 prime are the same thing. So many ways to say the same thing. So E3 denotes an event that at least one part does not pass. So here we have one part does not pass, the second one. Here we have one part does not pass, the first one, but at least one part does not pass. So here we have two parts that do not pass. So therefore, if I wanted to demonstrate what E1 union E3 is, I'm going to look for everything together. So we have YY, YN, NY. So these two are there, and then NN. So E1 union E3, it's everything that's in S. It's everything. And then E1 intersect E3, that's going to be YN and NY. So some simple concepts there, not too bad. Now, I said we're pretty much going to be sticking to discrete examples, but here's one exception here. This is a continuous example: union, intersection, and complement. So we've got the sample space S. It's going to be the set of all values that are strictly larger than 0. And then we're going to have these two events that are on this number line, E1 and E2. So let's take a look here. Let's see why is E1 union E2 this description right here. So let me just kind of make a line, and then I think I'm going to use, let's see, I've got some couple of colored pens here. I think that might work. So for E1 union E2, let's go here. We have 10 up to 15. This is a 0. So let's make this, we'll go 10, 11, 12, 13, 14, 15, and then 16, and then it's going to go on. So I'll just put like some dots here. So let's take a look at this first part. Let's call this part A, B, C, and D. So for part A, E1 and E2. So what is E1? It's 10, including 10. So I'm gonna actually put a hard brace here. Up to 12, but not including 12. So that's E1. And then E2 is 11 to 15, which is, I guess I'll use a different color pen here. 11 to 15. So we've got right here, 11 up to 15. That's E2. And so if I want to see what E1 union E2 is, I'm going to use my yellow marker here. That's everything. So I'm going to go from 10, including 10, all the way up to, but not including 15. So this would be my set of E1 union E2. How about for B? E1 intersect E2. Well, maybe I'll just do A and B here on the same line. Let me just use orange. So now I'm looking for the stuff that they just have in common. So if I look and I see that E1 I have in my black pen here, E2 is that which is between these two red parentheses, then what they have in common is this piece right here, 11 to 12 with the soft braces right there. So that's going to be B. So hopefully you can see that. Now, how about part C? So we've got, let me redraw E1 and E2, or maybe, I don't know if I want to do that just yet. Hang on a second here. 12, 13, 14, 15, and say 16, and then it goes on and on. So now we want E1 prime. So E1 is between 10 and up to and including 12. So E1 prime is everything that isn't E1. So that means we would go from 0 up to, but not including 10, and then everything above 12 and including 12 right here. So that would be a representation of E1 prime. So, and that's what you can see here. We have 0 to 10 right here, and then 12, including 12, and then going on forever there. And then finally for part D, and again, I'll draw this. Kind of wish I had had this pre-drawn, but that's okay. Okay. This one says E1 prime, so we've got a picture of that right here, intersected with E2. So what was E2 again? So E1 prime, let's do it this way. This is E1 prime. And then E2 was 11 to 15. So I'm going to use a red pen here. So we'll have 11 up to 15. And they want to know what is the intersection of that. And hopefully you can see that the intersection, that which this and this have in common with this, will be the 12, including the 12, and up to, but not including the 15 here. So this will be part D. I do encourage you, as you're watching the videos, either in class or, here like this, to use a bunch of colored pens. You're going to see me introduce a lot of color here in the upcoming lectures. So I'm going to stop this video right here at slide 7.